Well, good morning. It's 11:37 on the 26th, Tuesday, the 26th of February, 2019. It's supposed to be linear algebra class, but right now I'm the only one in the room. I'm 6 minutes late getting started. I apologize for that. But I had sounded like two or three messages from my wife, call as soon as possible. While I was in class this morning, I've tried to call her during my 15-minute break between classes, and I could not reach her on any of the phones that she's normally accessible at. So I brought my phone in today. I hope I won't have to take a call. I left her a message saying that I would have it with me, so I don't know. I hope it's not anything super urgent, but evidently I can't reach her now. So we'll get going and get started with class. Let me make just a couple of announcements first. Wait. Yeah, okay, I want to make sure I was recording. A couple of announcements first. I don't know if you recall, but last Friday I was not on the Birmingham campus like I normally am because I was here. We were making up a pre-calculus algebra class that I had missed the previous Tuesday because it was last Tuesday because I had a doctor's appointment that day. So we made that class up Friday morning, and then I was here the rest of the morning. Well, that was the first of 4 sort of messed up Fridays. This coming Friday, I have a dermatology appointment at the Kirkland Clinic, actually at the Whitaker Clinic, right next to Kirkland. And that's at 9:15 on Friday morning. So I haven't worked it out with my boss yet, what he wants me to do, whether I should come in, I can be on campus before 8, but then I have to leave by 8:45 to go to the clinic, to be there by 9:15, then to go back after it's over, hopefully no later than 10:15, maybe get back to campus by 10:45. I'll be on the Birmingham campus. As soon as the doctor's appointment is over with, I can get back to campus. I'll be there and be there until the early afternoon, whatever time that turns out being. Okay. I just don't know if I'm going to be there early in the morning or not. It seems sort of ridiculous to drive a half hour, be there 45 minutes, drive a half hour back, have the appointment, drive another half hour there, and then stay the rest of the time. So I don't know. I'll find out later, but hopefully by Thursday I'll know. So that's this Friday. I'll be on Birmingham campus at least the latter part of the morning, but I don't know what time that'll start when I can get out of the appointment and get back to campus. Okay, the following Friday, that would be the 8th, I've been asked or told to be on what they call the articulation meeting for the state, and that's going to be down in Mobile. So on next Friday, I will have to leave home as soon after 7 in the morning as I can to drive the 4 to 5 hours to get to Mobile, and then I should be there before noon. The meeting goes from noon till 3, and then I turn around and drive back home another 4 to 5 hours. So driving 8 to 10 hours to be for a 3-hour meeting, it doesn't seem like it makes a lot of sense, but they said I'm supposed to be there. So that'll be next Friday. Then the Friday after that, I have an eye appointment, and that's right across the street here at Birmingham West Hospital. I had thought it would be at the Eye Foundation Hospital, but they said, no, Dr. Swanner, who I'll be seeing, will be on investment that day. And I said, well, that's fine. That's right across the road from where I work. So I will be there. That appointment's at 8:15, so I'll come to campus, walk across to the appointment, have my eye examined, and then I'll come back to this campus, and then if I need to, I'll go back to Birmingham, but it seems like unless there's some reason to go, I think I'll probably stay on Bessemer, partly because there's just a half-hour driving that I can't get anything done, and the other reason is if my eyes are really highly dilated or whatever they're going to do to them, and then that's could be problematic when driving. Usually they give you really dark shades and you can drive okay, but I still don't like doing it that much, especially if they're bothering me. So that Friday. And then by that time, we're awfully close to spring break, but that'll be here or there. We'll figure that out then. Okay. Those are the major announcements I know about. Again, if I do have to pause the class in case my wife calls, then I'm going to do that. But otherwise, let's get going. All right. We're on in Chapter 2, which is Matrices, 2.2. Title of this is Properties of Matrix Operations, and we were on example 9, top of page 58. Okay? And it's one sort of similar to what we've done before, I think, in the little discovery thing we did on the previous page, but this time they give us these two matrices. Matrix A, let me get my pen set up. Matrix A is 2, 1, negative 2. Negative 1, 0, 3. 0, negative 2, 1. Okay, matrix B. 3, 1. 2, negative 1. 3, 0. Okay, I wrote those a bit too close together, but those are 3 columns. That's not subtraction on the middle. Okay, what we're to show is that AB transpose is the same as B transpose A transpose. Okay, so let's first do AB. Okay, first, before we even try, can you do AB? Well, A is a 3 by 3, B is a 3 by 2. Yes, you can, because those two middle numbers are equal, and that will give you a 3 by 2 result. So that'll be 1, 2, 1, 2, 1, 2. There's going to be the result of AB. All right. The first entry, the 1, 1 entry, will be row 1 from A, column 1 from B. That would be 6 plus 2 is 8, minus 6 is 2. Okay. The 1, 2 entry, first row of A, second column of B, 2 minus 1 would be 1. So that would just be 1. Then the 2, 2 entry down here is second row, 2, 1 entry, second row, first column, negative 3, 0, 9. That would be a 6. Okay? The 2, 2 entry here would be second row, second column, negative 1, 0, 0. That's just a negative 1. Then the 3, 1 entry here, third row, first column, third row of A, first column of B, would be a 0, minus 4, plus 3. That would be a minus 1. And the last entry is the 3, 2 entry, third row, second column of B. That would be a 0, 2, 0. All right. So there's AB. But they didn't ask for AB. They said AB transpose. So AB transpose, those are parentheses, supposedly I put brackets, would be exchange the rows and columns. That would be a 2, 1 on the first column, a 6, negative 1 on the second column, and a negative 1, 2 on the third column. All right. Now they said, show that that's the same as B transpose A transpose. Well, B transpose would be first column 3, 1, second column 2, negative 1, third column 3, 0. A transpose, on the other hand, is going to be a 3 by 3, and the first, I'm going to do it differently this time, first row would be 2, minus 1, 0, second row 1, 0, negative 2, and the third row negative 2, 3, 1. Can you multiply those? Well, this is a 3 by 2. No, sorry, 2 by 3. 2 rows, 3 columns. This is a 3 by 3. So that will work, and that will leave a 2 by 3. Okay. Now let's socket to it. The 1-1 entry here would be first row of B transpose, first column of A transpose. That would be a 6, and 2 is 8, minus 6 is 2. Okay. The second entry will be a 1-2 entry. First row, second column would be -3, 0, 9. That would be a 6. Okay, so far so good. The 1-3 entry of the product will be the first row of B transpose, the third column of A transpose. 0, -4, +3 would be a -1. Okay. Then the 2-1 entry of your product will be the second row of B transpose, first column of A transpose. That would be a 2, -1 would be 1, and that leaves you just a 1. The 2-2 entry will be second row of B transpose times second column of A transpose, -1, 0, 0. That would be a -1. And then finally, the 2-3 entry of your product will be the second row of B transpose times the third row, for the third column of A transpose. That would be 0, 2, 0. So it's just a 2. Sure enough, these two are the same. Okay? Those two are exactly, precisely the same. So that verified what we were doing earlier, that and it's the same answer they got in the book too. Good for them. That was the property that we did last time. Property of transposes. This was number 4. AB transpose, product AP transpose is the same as B transpose times A transpose. All right, let's move on to example 10. Okay. For the matrix 1, 3, negative, let me write it down. Matrix A, 1, 3, 0, -2, -2, -1. Okay. Find the product A transpose and show that it is symmetric. Okay. So we need to know the product A transpose. Well, what we need first is A transpose. Okay. Well, A transpose is that's going to be A is a 3 by 2. A transpose is going to be a 2 by 3, and its first row will be 1, 0, -2. Its second row will be 3, -2, -1. Exchange the rows and columns. Now it says multiply them. Can you do that? Well, let's see. This is a 3 by 2 times a 2 by 3. Sure enough, we can, because the center, middle values are the same, and that will give you a 3 by 3 as a result. And let's see what you get when you multiply them. The 1-1 entry will be first row of A times the first column of A transpose. 1 plus 9 is 10. The 1-2 entry here will be first row times second column. That would be 0 minus 6. The 1-3 entry here will be first row by third column. -2 minus 3 is minus 5. The 2-1 entry here will be second row by first column. 0 minus 6. The 2-2 entry here will be second row by second column. That would be 0, 4. And the 2-3 entry here will be second row, third column. That would be a 0, 2. Okay. Sorry. I grabbed the granola bar in between classes. I got something stuck in my teeth, and it's hard for me to move my mouth around now. So, sorry. I'll get it back. All right. The 3-1 entry down here is going to be third row of A times the first column of A transpose. That'll be a -2 minus 3 is -5. The 3-2 entry here will be third row times second column. That would be a 2. And the 3-3 entry here will be third row, third column, third row of A, third column of A transpose. 4 plus 1 is 5. Okay. Now, that was the first part. It says show that it is symmetric. Well, again, it doesn't matter what the main diagonal is. But other than that, your opposing entries here are identically the same. The 2-1 entry is the same as the 1-2 entry. The 1-3 entry is the same as the 3-1 entry. And the 2-3 entry is the same as the 3-2 entry. They're identically the same. It is a symmetric matrix. Doesn't matter what that main diagonal is. Okay? Last time we ran across a symmetric matrix, I was trying to remember what that was. That was C transpose on page 57, example 8C. Those had all 1s on the diagonal. They don't have to be. Okay? Was there another? I think that may have been the first one. Of course, you know, all our identity matrices are symmetric too. But this is just to emphasize, note that the square matrix in part C on the previous page is equal to its transpose. Such a matrix is called a symmetric matrix. The matrix A is symmetric when A is equal to A transpose. From this definition, it should be clear that a symmetric matrix must be square, and ours is. Also, if A is Aij is a symmetric matrix, then Aij is equal to Aji for all i's not equal to j. If they're equal, that's on the diagonal. They don't have to be the same. But if they're off diagonal, then they must correlate to the opposite one. Okay. Now, and they got the same thing we did: 10, -6, -5, -6, 4, 2, -5, 2, 5. Okay. Now, so any matrix A that you multiply by its own transpose, you will come up with a symmetric matrix. And notice that A and A transpose didn't have to be squared, but their product has to be squared. If you had multiplied the other way, of A transpose times A, you would have also gotten a symmetric matrix, but that would have been a 2 by 2, because it's been a 2 by 3 by a 3 by 2. The middle numbers equal, take them out, and that would be a 2 by 2. But that would be symmetric also. In that case, only the 1-2 entry would equal the 2-1 entry. That's the only thing that's required. In a 2 by 2, one pair has to be equal. All right, there's a linear algebra applied at the bottom of page 58. That's information retrieval systems such as internet search engines. The most famous, I guess you would say, one would be Google. That's how they made their name and made their money and made their hold on and the technology industry. But they came up with a search program that was just so much better, so much faster, so much everything than all the others. That's what put them on the map. Okay, so search engines use linear algebra, surprise, surprise. Okay, so homework exercises 2.2. Do any of the odds 1 through 5? They should all be at calcchat.com. And by the way, the answers of the odds are in the back of the book as well. But then if you can't figure out how to get that answer, you can go to calcchat.com for worked out solutions to these odd number problems. So that's why I give you odd numbers. So any of the odds 7 through 11. Do number 13. Has 4 parts. Do any of the odds 15 to 19. They're all at CalcChat. Do 21, it's a CalcChat. Do 23, it's a CalcChat. Do 25, it's a CalcChat. Do 27, it's a calc chat. Do any of the odds 29 to 33, they're all a calc chat. Do 35, it's a calc chat. 37, it's a calc chat. Either 39 or 41, they both should be a calc chat. 43 or 45, they should both be a calc chat. 47 is a true-false question. You won't see many of these on a test, but it's good to think through. 49's one you could do. You can do 51. Hopefully, you won't multiply that 19 times, okay? To do 51, I would say go back to page 56 when they give you the setup for and the definition for the power of a matrix. They do it sort of obliquely or indirectly, but I think you can see it there, and hopefully you'll figure out a way to do that without doing that many operations. So that's 51. Try 53. That should be at calc chat. 55 should be at calc chat. 57 is a guided proof. 59, 61, 63 are proofs. You can do them if you like or not. That's up to you. 65 is a guided proof. You can decide whether you're going to do that or not. 67, 69, you should be able to do those. They should be at calc chat. 71 and 73 are two more proofs. Again, you decide whether you want to do that. 75 is one of these unusual matrices they use to try to teach you something. So try that if you like. If you don't, that's fine too. So let's move on to inverse of a matrix, which is 2.3. Finally through with 2.2. Inverse of a matrix. All right. Now, we've talked about functions having inverses. Trig functions have inverses with limited domain. What do we mean by the inverse of a matrix? Well, here's where the need or the idea comes from. Let's think of a simple linear equation, really simple. AX is equal to B. Excuse me. Now, what you can do to solve that equation for x is, of course, divide by a. Divide both sides by a, and which you'll notice is the same thing as multiplying by 1 over a. That's the same thing. You don't have to be dividing by a, it's multiplying by 1 over a. Well, what is 1 over a? A is the reciprocal of a. 1 over a is the reciprocal of a. So then you're multiplying both sides by reciprocal of a. Okay? So reciprocal of a, and when a is a number or a variable, and you put the -1 there, that means reciprocal. So a reciprocal times x is equal to b times a reciprocal. Okay? This multiplies to be 1, because 1 over a times a, the a's divide away, and you're just left with 1. So then you have x is equal to b times the reciprocal of a, or b over a. Okay, if you want to express it that way. Okay, that's pretty straightforward. Now with numbers, where you write that doesn't matter. The book wrote it as reciprocal of a times b, which of course is the same thing as the a b times reciprocal of a in numbers. But when you deal with matrices, you have to be a lot more careful. Okay? The number a to the -1 is called the multiplicative inverse of a, because a to the -1 times a is 1. Okay, the identity element for a multiplication. The definition of multiplicative inverse of a matrix is somewhat similar You just have to be careful which side you add or, you multiply by, because that does make a difference. So, let's clear this air screen for everything that's on here. And let's do, here's the definition of the inverse of a matrix. First, in order to have an inverse, the matrix must be square. N by N matrix must be square. A. That matrix A, N by N matrix A, is what we call invertible. In other words, it's capable of being inverted. Another name for that, and this is a rather strange one, or non-singular. Okay? To be invertible is to be non-singular. To be non-singular is to be invertible. Mean the same thing. One sort of a positive sounding thing, one sort of negative sounding thing. Okay? But this matrix is invertible or non-singular when there does exist another N by M matrix, when there exists another N by M matrix, and it will also be square, and it'll be the same dimension, N by N, matrix B, okay, such that, vertical line usually means such that, A times B, and if they're the same size, same square size, N by N, they certainly will multiply and produce an N by N, and that is equal to B times A. If this is the case, okay, there will be this other matrix, N by M matrix B, such that AB is the same as BA, and that is the same as I sub N. Whoa! That means there's got to be some matrix that's going to, when you multiply it by its inverse, will give you the identity matrix. Now catch the picture here. A multiplicative inverse, 1 over A times A. Now, don't get the idea that the inverse matrix is a reciprocal. It is not. Nowhere close. Okay? But we use that same symbology. So 1 over A times A, of course, is 1. Okay? Well, where A is the multiplicative inverse of A to the minus 1. In other words, reciprocal. Okay? Well, in matrix speak, A and B, if A is an invertible matrix, N by N, then there is a B that's N by N also, such that AB is the same as BA. Remember, most of the time they're not. They're not the same. But in this case they are, and if that product is, either way you multiply them, the identity matrix of that same size, N by N, then these two matrices are invertible, and they're inverses of each other. Now, notice A times B, which is, we say, is the inverse of A, just like little a times the reciprocal of A, 1 over A, is equal to 1. These two, A times B or B times A, is equal to the identity matrix. So the identity matrix, again, sort of takes the place of the numerical value 1. Okay? In space, an identity matrix, of course, is always N by N, always square, and it will be the same size as Z. Okay. Now, that's your definition. Now, non-square matrices do not and will not ever have inverses. You have to have square matrices to have an inverse. The next theorem, 2.7, is the uniqueness of an inverse matrix. And basically what it's saying is if A is invertible, now what does that mean to be invertible? It means A has to be square, okay? Can't be anything other than square. Whatever size is fine. If it's invertible, that means there does exist some other b that when you multiply it by a, it will give you the, and the b has to be same size square matrix, and that'll give you the identity matrix of that same size. So, if A is an invertible matrix, then this means that its inverse is unique. In other words, ooh, the pen just hit the screen. Okay. If A, being a square matrix, is invertible, that means you can't have more than one inverse. Whatever inverse it is a unique inverse, and you can't say, well, that's one inverse, let's find another. No, there will be no other. Its inverse is unique. Okay? And the inverse of a matrix is denoted by, just like we did before, yuck. This is driving me nuts. Okay. The inverse of a matrix is given by that symbology. The same name, A, but put an inverse with it. Just like we did for reciprocals with numbers or variables, just like we did with functions, that the one undoes the other. This is what an inverse means. Okay. They give a little proof here, and this is a really simple little proof. What you're given here is A is invertible, which means there has to be some B out there that A times B. Hey. Okay, hold on just a second. That's good. I'm sorry, I was talking to the recording. Daniel's here. Just to show how weird a day it was, the reason that student was here is that we had scheduled a trip to the planetarium at Stanford University for my physical science class. Well, I finally was able to talk with the guy there, trying to confirm it Friday. He said, oh, I guess we didn't get you the word. We tried to send it out to everybody, but I guess it didn't get to you. The guy at the planetarium took a job at Huntsville at their planetarium at the Space and Rocket Center, so he's no longer at Stanford. His last day was yesterday, so we can't go on a field trip today because there's nobody there to give the field trip. So I had tried to arrange to substitute and put another field trip in the place because we're ready for a second one, and I can't get in touch with the people there at all. So last night, after failing again to get in touch with anybody, I sent Blackboard, sent the announcement that, the field trip was off and we're going to have class today. Well, good old school is changing their email server, and even though we have changed and we have to do things differently, Blackboard has not changed, and it's not sending emails when it's supposed to. And they said they got it fixed, and it's not fixed. So it's been that kind of day. And on top of all that, when I went to my office between classes, I had 15 minutes between to exchange a pre-calculus book with this book. I saw my phone, and I usually don't bring my phone to class, had a message, 2 or 3 messages from my wife, call ASAP, I called her the whole time I was down in my office. I called home, I called her cell phone, her office number, and I tried calling home, but our home phone must be out again. And so it's been a wacko day, just all the way around. So,
I've been having wacko months.
Yeah. Did you ever get your stuff straightened out?
I paid a little bit, and I got a hold right now.
Okay.
So until I know for sure I'll be able to pay it by the end of the semester.
Okay. And they understand that?
From my understanding,
Okay.
So I mean, I saw that the whole bid show up on the account now. So
Right.
I'm just gonna assume that what she told us was.
Okay. But it's because they sent an email to us last week saying, check to make sure everybody's fully paid. So you're going.
They say it fully.
Well,
I don't know.
that's the thing. I don't know either. But if you know that, if they know that you're working on it and you're making, I hope that's okay.
Okay.
I want you in class if you can stay in class. You know,
I want to be in class too.
Yeah, if
not at work in times.
Yeah.
Like I normally don't work in the morning. I normally work at night, but I've been trying to like pick up those shifts as I got to.
Right. Okay. Now, what we're doing, we finished 2.3, or I finished 2.3 earlier, and then Daniel just came in, 2.2, and we just started 2.3, and this is the theorem 2.7, bottom of page 62. Here's basically what it says. If A is an invertible matrix, that means it has an inverse, then its inverse is unique. And it's denoted by A inverse. Okay. Now, this is such a simple and straightforward little proof, but it's just like you'll see a lot of other proofs going, so I think I will do this one. Now, because A is invertible, that means there is an inverse, we're going to call it B, such that, and this is the earlier definition here, such that AB, and most of the time, okay, back off a moment. For a matrix to be invertible, it's got to be square. No doubt about it. You cannot have an invertible matrix that's not square. So it's got to be square. And its inverse is going to be square of the same dimensions, n by n, both of them, okay? Now, if A is invertible, you know there's an inverse B. And that when you multiply A times B, that's going to be the same as B times A. Now, if you think back earlier, for any old two matrices, A times B is usually not equal to B times A. I mean, they don't even have to be the same size. They just have to be the right size to multiply. But not only do these have to be the same size, but they have to be that A times B is the same as B times A. That makes it pretty unique. And what's more, you know the product of it, and that product is the identity matrix I. So you know that's going to be the case. Now, what if A did have another inverse? Let's say C. Let's say C is also the inverse of A. And let's say it's uniquely different from B. Okay? It says to show here that A and C have to be equal. That's going to show this. The inverse is unique. Okay? So, what we're going to do, we know that A times B, like I said here, A times B has to equal I. Okay? Now, what if you multiply on the right, no, left, on the left, by C, you also multiply I by C, right? Well, C times A, and you know that in matrix multiplication, as long as all the sizes are right, then you can do it in any order you want to. You can't switch them around, but you can do it in any order. So this would be the same as C times A times B, and that would be the same as C. Okay? CI, and CI is the same as C. Okay? But CA, you said, is also an inverse. That means this is I. Well, I times B then would be C. But guess what? I times B is B. This shows that B has to be C. No doubt about it. So consequently, B is equal to C. That means there's only one inverse for matrix A, and that is B, because B and C are the same. Now, we usually call this B A inverse. That is the name for it. That was up here, right here. The inverse is called A inverse. Okay? It's the inverse of A. Not just one of the inverses, it's the only one. And just like we said there, if that's what your A inverse is B is the A inverse, then we can rewrite this as A inverse times A is the same as A times A inverse, and both of those are equal to the identity matrix. All the time. Every time. All right. Let's do example 1. Any question on that? All right. Now, by the way, this 2.7 uniqueness of an inverse matrix, or somewhere starting here, we're going to start having all these different features of inverse matrices. Here's the first one, okay? Pretty simple, straightforward. From now on, we're just going to keep adding more and more things. Soon it'll be, if one of these are true, the other's true. And then if one of these are true, the other 2 are true. And then it's going to be, if any one of these is true, the other 4 are true. Yeah, it's going to keep growing like that. So get ready for that. I've got to find my cursor. There it is. Erase this. Let's do example 1. Okay. Here is a matrix A. It says show that B is the inverse of A. Well, here is A, -1, 2, -1, 1. And here's B, number 1. Can A be an invertible matrix? What is required for a matrix to be invertible? Say again? It has to be invertible, it has to have an inverse. What is required of A? Remember this from the other day? You weren't here, but you should. That is a square. It's supposed to be a square anyway. And there's a little story that goes with it. It's not quite. It's more like a diamond, but you know, try to make it a square. When I was growing up, I had an older brother and then a younger brother. My older brother was a pretty serious student, and you know, he had his irregularities, but he and I got along really well, just about all the time. But then along came our younger brother, and he was the rebel. Whereas we did well in school and stuff. He did okay. He did fine, but he just had to kick against the prods, just the whole time, And he was always stretching. And of course, parents get tired after the first and second kid. Soon the third kid can do anything they want to. And Dan took advantage of that. So when he got to be probably junior high, high school age, he considered me an L7, which to him was a square. And so he started calling me L7. And then it just became L. Hey, L. And to this day, every now and then he'll say, hey, L. Not even thinking about what that stands for anymore, but that's what he calls me, is L. Bizarre, but strange. So to be an invertible matrix, it has to be square, and it is. Now here's B. B, if it's going to be the inverse, it also has to be square of the same size. 1 minus 2, 1 minus 1. Now there's no guarantee that these are inverses of each other, okay? But we're going to see if they are. How do you see if they are? What's true about two matrices that would be inverses of each other? When you multiply them, you get the identity matrix. Every time. Has to. Okay? Now, can these two be multiplied? What size is A? 2 by 2. What size is B? 2 by 2. And as long as these middle values are the same, it is, and then this one will also be, what's left over on the inside and out, or the outsides of both of those will be a 2 by 2. Of course it has to be the same. So let's see what we get when we multiply these two together. So how to multiply? This first entry here is the 1, 1 entry first row, first column. So when you're multiplying, you take the first row of A times the first column of B. Okay? Yeah, that would be a negative 1 times 1 plus a 2 times 1. Well, negative 1 times 1 is negative 1 plus 2 times 1 is 2. Negative 1 plus 2 is negative 1 plus 1. Okay? Now, the next entry is the 1, 2 entry. So you take the first row of A again, but now the second column of B, and you multiply those together. Negative 1 times negative 2 is?
2.
Second? 2. Plus 2 times the negative 1 is? Negative 2, and that adds to 0. Okay, so far so good. Now this entry down here is the 2, 1 entry. Second row, first column, so you take the second row of A times the first column of B. Well, what does that give you? Negative 1 is 0. So far, so good. And now this last entry is the 2, 2 entry. So you take the second row of A times the second column of B, and what does that give you?
2 plus negative plus negative 1. So that'd be negative 1.
Do it one more time.
2 plus 1 would be 1.
1. All right. And that indeed is the 2 by 2 identity matrix. 1's down the diagonal, 0 everywhere else, which is just 2 other places. So sure enough, those are inverses of each other. Now, that alone probably is enough, but usually what we do is check and make sure that B times A is also the identity matrix. So if we rewrite A over here to be minus 1, 2, minus 1, 1, let's see what we get if we multiply B times A. This is A times B. Let's do B times A. Can you multiply that? Yep. A is, again, 2 by 2, and these middle two are the same, so your answer is going to be a 2 by 2. 1, 2. Oh, excuse me, I got the hiccups. 1, 2. All right, and again, you do the 1, 1 entry, which is the first row of B now, times the first column of A. And what do you get?
Negative 1 plus 2.
Yes.
It's 1.
1. Perfect. And if you do, the second entry is the 1, 2 entry, so it'll be the first row of B times the second column of A. And that would be?
2 plus 1.
At?
Oh, wait. You said, oh, no. Negative. It would be 2 plus negative 2. So it would be 0.
0. Perfect. Okay. And then the next entry is the 2, 1 entry, so it would be the second row of B times the first column of A, and that would be?
Negative 1 plus 1, 0.
0 again. And then the 2, 2 entry would be the second row of B times the second column of A, and that would be?
2 plus negative 1.
What would that be?
1.
1. Perfect. So sure enough, they're equal to each other, which most of the time, what's the word? Commuting two matrices together will usually not give you the same result, but if they're inverses of each other, they do give you the same result, and that result is always the identity matrix. Okay, and we've shown it both ways. So let's do example 2. Okay, we'll erase all the ink here. Now it says find the inverse of A, and A is 1, 4, negative 1, negative 3. Oh my word. Find the inverse. Well, number 1, what size would it have to be? A 2 by 2, it's got to be. So what you want to do, maybe name these elements. I'll do it the same way they do. X11, X12, X21, and X22. I was real tempted to call it A, B, C, and D. To me, that's easier to write, but they're doing it this way, so I'll do it this way. Now, That's supposed to be the inverse. That's what we're looking for. If you multiply those two together, what's it guaranteed to give you as a result? Not the inverse, identity matrix. 0, 1, 1, 0, 0, 1. Okay? Well, guess what? We can do that multiplication and come up with a result, and let's see what we get. Okay? When we multiply these two together, we should get that. So that would be 1 times x11, so that would be x11 plus 4 times x21, and that should equal 1, right? The 1, 1, first row by first column here, okay, should give you that value right there, right? Okay? Give me another equation. First row by second column, that would be x12, 1 times x12, plus 4 times x22. Whoa, wait. Goodness gracious, I can't believe I did that.
Oh, my bad, I was right with you.
Okay. Whew, goodness gracious. I wrote it on top of it. Okay. The first one would be x12 plus 4 x22 is equal to 0, because that would be the 1, 2 entry, right? Give me another equation.
Row 2, column 1.
Is what?
Row 2, column 1.
Right.
And it would be x11.
It's a negative, isn't it? This times this. Second row by first column. Negative x11.
Plus.
I think it's going to be a minus, isn't it?
Oh, yeah. Negative
3x21. Okay. And that equals 0. And then the fourth equation would be?
The second column in the second row. So that would be 4.
Second column, second row. Second row, second column.
Oh, my bad.
Row first column. Okay.
It's how it looks like that.
Yeah.
It'd be negative x 1, 2.
Right.
No, it's 2, 2. It's weird to look at. That's what I'm saying. Like, it's just weird to look at. Like,
yeah.
You should have did them by ABC. I would do them.
I know that's so much easier. But it's this one: minus x12 minus 3x22 is equal to 1. The 2, 2 column. Okay. Now, there is a sort of easy way to do this. Unfortunately, I don't think they're going to do the easy way to do this. Now, actually what they did, believe it or not, they did what I was, oh no, they did, okay. They wrote it as a matrix and put, let me see, I have an extra plus sign in there. It looks really weird. Okay, left over from before. They write this as the 1, 1 entry. This is the 1, 2 entry. This is the 2, 1 entry, and this is the 2, 2 entry. Okay, as a matrix, and they set them equal to that. So this is no better, but it's I don't think any worse either, but this would be x11 plus, my screen's moving on me, 4x21. Okay, that's going to be the 1 there. And then the x12 plus 4x22 here, that's going to be your 0 there. And I'll take off that line there. I'll put it in there for a reason, trying to get your attention to something, but I don't need it anymore. This will be a minus x11 minus 3x21, and this would be a minus x12 minus 3x22. Okay. That's just another way of writing that same equation we did. Okay. Then they go back and write it this way. I mean, they're just going all over the place. Solving the first system, which is these two, okay, you can solve that by adding them together. Okay? If you add this one to that one, these two, notice your x11s will disappear. And this gives you an x21. Because 4 minus 3 is 1. Okay. So x21 is equal to, and when you add these two together, this one and that one, and these, that gives you a 1. So x21 is equal to 1. All right? Got that one done. Okay? From that one, you can kind of back up a little. Well, let's go on and do the next easy one. Add these two together, and again, these two add to 0, and this gives you x22, because plus 4 minus 3 is 1, and that's also equal to 1. So your x21 and your x22 are both equal to 1. Okay? Now, trying to think if anything else is easy. I think what you do then is go back and plug in. If x21 is 1, this is saying that x11 plus 4 is equal to 1. So that means x11 is equal to negative 3. And down here you say is either one of these easier than the other? I don't guess so. x21 is 1. I mean, x22 is 1. So this would be, all right. I think I've seen them before somewhere. I'm trying to recall where that was. Okay. Okay. We're in 2.3, and we're just beginning to reach out to do the inverse of a matrix. And it involves matrix multiplication. Have you followed enough to know how to do matrix multiplication? Okay, good. Okay. Well, what we're doing is solving for the last thing. So what I had here was x22 is equal to 1. And if you knew that to be the case, you could either substitute in here or here. I think I like this better. So this would be x12 plus 4, I think is equal to 0, right? Yeah, x12 plus 4, because 22 was 1, so x12 plus 4 is equal to 0, so x is equal to minus, x12 is equal to minus 4. Okay, so Now we've got all four of our values here. Whoops. Drew right over that one. Okay. So what your unknown is, this matrix here, x11 was -3, x12 was -4, x21 was -1, and x22 and that, x22 is 1. Okay, I couldn't find it. Okay. All right, so this is your unknown matrix. -3, -4. Ooh, where did I get a -1? That's a 1 right there. Okay, sorry. That's a 1. 1, 1. Okay. Now it says try using matrix multiplication to check this out. In other words, oh, and this, by the way, this they called the X matrix, but it's also A inverse because the product of that and A gave you the identity matrix. All right. And it said, try matrix multiplication to see if it works. Well, we can do that from where we're sitting, can't we? First row by first column here would be -3, right? +1. +4 is 1. Yeah, that's right. Let's do first row by second column. And that would be a -4 + 4, 0. Yeah, that's right. And then do the 2, 1 entry, second row, first column, first column. That would be -3 + 3. No, +3 - 3 is 0. That works. And then do the second row, second column. That would be +4 -3 is 1. So sure enough, that does give you the identity matrix. All right. Now, they says generalizing the method used to solve example 2 provides a convenient method for finding an inverse. Okay. I don't know if this is intuitive or not. Note that there's two systems of linear equations, and I wrote them like this. They wrote them in pairs, okay? On top of one another, but take these two. This is 1, 4, -1, -3. That's exactly A here. Okay? Multiply it by 1, 1, 1, 2. Okay? 1, 1, 1, 2. Take this and multiply it by the first column here. Not in matrix multiplication, but in Gauss-Jordan elimination type thing. Okay? And that was basically what we were doing here when we were adding these two together and making this row. You know, that's exactly what we were doing with that. Getting those to equal first the first column and then the second column. But the second column was using these, this matrix, to get the second column, okay? 0, 1, because you see this, that multiplied to be 0, 1, okay? Now, here's what basically you wound up doing. Okay? I'm going to try to shorten this a little bit because they just draw out more and more and more, and it doesn't get any clearer when they do that. If you were to take that first matrix, the matrix A, and we'll start by this, 1, 4, negative 1, negative 3. Okay? And adjoin that, I'm going to take off the equal sign here and take off that bracket too. Adjoin that with first 1, 0, that's the first column of the identity matrix, and then we're going to do it with the second column of the identity matrix. Okay? So basically what you're doing is the given matrix A, which is here, and adjoin that to the identity matrix, which is what you're going to try to get. Okay? Now what you're going to do are the row operations here to make this the identity matrix, but you're going to do it to this too, and what's going to come out is what you got at the end, which is the inverse matrix. So let's see if that is indeed making sense. Okay? All right. To do Gauss-Jordan elimination, we want that first entry to be a 1. We got it. Thank you very much. It's already there. Right? Now, what we're going to do to make, what do we want this to become? A 0. And easy to get it, row 1 plus row 2, right? Becomes 0. So we leave the first row alone, 1, 4, 1, 0. Let's do what we just said. Add the two together, and that will be the new row 2. 0, 1, 1, 1. Okay. Now, we've got the first entry exactly like we want. We've got a 0 below it. And the second entry is exactly what we want. A 1 there. Now we want that to be a 0. How do we make that happen? Do the opposite of this times this and make that the new, and add it to row 1. R2 plus R1. My screen collapsed on me. Yeah. If you multiply that by -4 and add it to the top, the top becomes a 0, right? Okay, that's what we're going to do. So let's do it everywhere in the row. So this would become, we're keeping the bottom row 0, 1, 1, 1, and the top row becomes, that stays a 1. The next becomes 0. That better be what it comes. Next. Say again. -7, is that what you, huh? Negative, okay. -3, got it. Yeah. -3. And then the next one? -4. Okay. I sort of lost my elevation here. It sort of started flying away on me. That want everything to go. Okay. Whew. All right. Now, what do we say from before our matrix was? -3, 4, -4, 1, 1. That's exactly what we got here. That is your, when you put the matrix A here, multiply it by the I matrix, identity matrix, when you wind up with identity matrix here, this will be A inverse. That's exactly what we got. So there's the, I don't want to say easy way, but sort of the straightforward way of doing finding the inverse of a matrix. I am so sorry. All right, and they wrote the same thing I did. You start out with AI, you wind up with IA inverse. Okay, so here's the procedure, finding the inverse of a matrix by Gauss-Jordan elimination. Of course, A has to be square. If A is not square, don't even bother. It's not going to have an inverse. And it's of order n. Okay. Let's see. Have we already gone over time?
Yes.
I'm sorry. We'll have to stop there.
already doing that, so I thought you wanted to finish before I...
Yeah, I'm sorry. We'll review that next time. We'll stop right there at the this finding the inverse of a matrix. Sorry, I didn't mean to go over the main reason. I've got a class coming up in less than 30 minutes. I need to try to grab lunch. I have another class coming. All right, let me end this. What's that?
Those tests.
Oh, the first test? Yeah. I couldn't remember if you had been here or not. All right, you too.
And do you have any problems or
What's that?
do you have any more problems or?
Oh, I'm sorry, I didn't say that. Let me say it. This has been a crazy day. I'm just wrapped up. All right, homework exercises in this section. We didn't get many done, but I think you can do 1 through 5. Any of the odds 1 through 5, they're all at Calc Chat. And you can start doing 7 through 11. We won't do the others until we get those done, but do 7 through 11. No, yeah, 7 through 11. Odd numbers.
Yeah, I want the differential equation.
I'm sorry?
Differential equation.
I don't have it up here. If you want to come down to the office with me, we can get it there. Okay.
I got Cal 3.
What's that?
I got the one from Cal 3.
You did?
Yeah. I got it. It's at home.
Okay, yeah. So that's the only,
There's only 3.
yeah, there's only 2.
Did you give another test out?
No, we're in Chapter 2 now. And we're in Chapter 2 in differential equations also. And let's see, are you also in Cal 3? We have done one test in that. Did you get that one?
Yeah, that's the one I got.
Oh, but you don't have differential equations. Oh, okay, right, okay. Because okay. Let me end this.